Okay, so welcome back to another video. So in today's video, we're going to be calculating this limit, the limit as k approaches infinity of k squared multiplied by the k plus 1 root of pi minus the k root of pi. So judging from this, I can already tell that it looks like we're going to have to take some logarithmic differentiation. So that's one thing's for certain. So let's actually do this. Let me actually restate our given problem and define that as L. So L is equal to the limit as k approaches infinity of k squared multiplied by the k plus 1 root of pi, and then subtract that with the k root of pi. So now I want to rewrite this limit with using this algebraic property. So really, this k squared, well, this whole expression here can be rewritten as the following. So the limit as k approaches infinity of our numerator will actually be the square root of, or the k plus 1 root of pi. Then subtract that with the k root of pi. And then I'm going to divide this by 1 divided by k squared. That's the algebraic property that we can use for this. Okay. So now also notice that well, not just yet. I can actually rewrite. So I can rewrite the k plus 1 root of pi as pi equal, or pi to the power 1 divided by k plus 1. That's equal to k plus 1 to the root of pi, and then same thing for the k root of pi. That's equivalent as pi to the power 1 over k. Okay, so notice that pi to the power 1 divided by k plus 1, that actually approaches to 1 as k approaches infinity. And this is because if I were to take k approaches infinity, so 1 over infinity, that's going to converge to 0. And so pi to the 0 power, that's going to equal 1. And then the same thing can be said for pi for 1 over k. That's going to converge to 1 as k approaches infinity. Same thing as before, 1 over infinity is equal to converges to 0. So pi to the power 0 is equal to 1. And then over here is 1 divided by k squared. So 1 divided by infinity, that goes to 0. So in case you notice, this is actually a 0 over 0 indeterminate form. Okay, so that's indeterminate form. So therefore, we actually want to use L'Hopital's rule to calculate this limit. So I'll write apply L'Hopital's rule, and that says, I'll write it over here actually, keep going. And that says that if the limit as k approaches infinity of some f of k divided by g of k, if that's a 0 over 0 or infinity over infinity, then we get that this is the limit as k approaches infinity of f prime of k, and then divide that by g prime of k. Okay, so that's what we're going to do. So we're going to take we're going to actually take the derivative of the numerator and take the derivative of the denominator. Okay, so let's do this one by one. So let me actually write out what we need to do. So that means limit approaches infinity, and then we're going to take the derivative with respect to k of pi to the power 1 k plus 1, subtract that with pi to the power 1 divided by k, and then divide that with the derivative with respect to k of 1 divided by k squared. Okay, so that's what we need to do. Okay, and then now pi to the power 1 over k plus 1 and pi to the 1 over k, we can write this, we can actually rewrite it so the equality is written in forms of the natural logs, well really with the base of e. So in other words, so I'll put a star over here. So pi to the 1 k plus 1 is equal to e to the power the natural log of pi to the power 1 over k plus 1 but I can actually move, since 1 over k plus 1 is treated as an exponent, so I'll just move that out to the front. So really this is e to the power 1 over k plus 1, and then multiplied by ln of pi. Okay, and then the same thing can be said for 1 over pi to the power 1 over k. So that's written as e natural log of pi 1 over k, and then I'll move the 1 over k to the front of the natural log, so this is 1 over k, then multiplied by ln of pi. Okay, so now I'll just replace that with our substitutions. So in other words, this is the limit as k approaches infinity of the derivative with respect to dk of, let's see, pi to the 1 over k plus 1. So that's e to the power, so I'll put natural log of pi as part of the numerator, divide that by k plus 1, and then subtract that with over here. So this is e to the natural log of pi, and then divided by k. Okay? And then divide this with the derivative with respect to k of 1 divided by k squared. So now this means we have to take the derivative of both the numerator and denominator. Using linearity, I can actually do separate derivatives. So take the derivative of the first one and then subtract that with the derivative of the second. So therefore this means now we gotta calculate our derivatives. So we're really just gonna focus on the, okay, so now we just have to focus on calculating the derivative. So, okay, I'm gonna do this one by one. So first let's calculate the derivative of e to the ln of pi divided by k plus 1. Okay, so you know that derivatives of some e to the power x sum to some variable is defined as the same thing, e natural log of pi divided by k plus 1, and then that's multiplied by the derivative of our exponent. So the derivative of what is it, the natural log of pi divided by k plus 1. Okay, then this means we need to use the quotient rule to evaluate our derivative. So let's see, so derivative, the product rule says that it's f prime multiplied by g, subtract with f multiplied by g prime, and then divide by g square. Okay, so let me write this and then multiply. Okay, so obviously g square is going to be k plus 1 squared, that's on the denominator. Okay, so now we just need to calculate the derivative from the numerator. So f prime, so ln of pi is a constant, so it's just 0 multiplied by k plus 1 is 0, and then minus ln of pi, and then multiplied by the derivative of g with respect to k, that's just 1. So this is just negative ln of pi. So then this means this is equal to the negative ln of pi, and then I'll just substitute our e ln of pi divided by k plus 1 back with pi over 1 plus k, which we said that that's the same thing as this. So this is multiplied by the k plus 1 root of pi, and then that's being divided by k plus 1 squared. Okay, so that's one derivative down. So now we just have to calculate the other one. So now next we need to calculate, let's see, the derivative with respect to k of e to the ln of pi and divided by k. Okay, so same thing, e ln of pi divided by k, and then multiplied by the derivative with respect to k of ln of pi divided by k. Therefore, let's see, e ln of pi divided by k, and then so I know that the denominator k squared, and then derivative of ln of pi is just 0 multiplied by k it's just 0. Then subtract that with the natural log of pi multiplied by the derivative of k, which is just 1, so we get that it's negative ln of pi. And then I'll substitute back our natural log, or e natural log pi divided by k with back here, which is pi to the power 1 over k, which is the same thing as the kth root of pi. So this is the negative ln of pi, k root of pi, and then divided by k squared. Okay, now next is to calculate our derivative of 1 divided by k squared, and then use the quotient rule. So this is going to be k to the 4th on the bottom. Derivative of 1 is 0, then multiply by k squared at 0, and subtract that with 1 multiplied by the derivative of k squared, which is just 2k, so minus 2k. You simplify this out, the k's cancel, so we get that this is just negative 2 divided by k to the cube. And now we just plug everything back in. So this is the limit as k approaches infinity of, let's see, so this is the derivative of here, so this is the natural log of pi divided by, multiplied by k plus 1 root of pi and divided by k plus 1 square. Then subtract from here, but that'll become an addition, so this is natural log of pi k root of pi and divided by k square. Okay, and then all this being divided by negative 2 to the power k cube. And now next, what I want to do is now I actually want to factor out the ln of pi. Not only that, since there's the leading term here is negative, I'm just gonna move, or well, switch the terms around. So this goes behind and then this goes to the front. It's still addition, so it's addition, so it's commutative. Okay, so infinity, and multiply that out by ln of pi, and then multiply by so if I factored this out, k root of pi divided by k squared, and then subtract that with k plus 1 root of pi divided by k plus 1 squared. And then this is divided by negative 2. Now notice that we state that earlier that pi to the 1 over k plus 1 converges to 1, and then as k approaches infinity, and pi to the power 1 over k converges to 1 as k approaches infinity. So that means I'll just rewrite this as, so ln of pi, and then multiply by 1 divided by k squared, and then minus 1 divided by k plus 1 squared, divided by negative 2 k cubed. So with that, now let's actually fix our fraction over here. So let's actually reduce this, or not reduce, but let's get a common denominator. So I have, this is 1 k squared minus k plus 1 squared 1. It means we get a common denominator. I get that this is k squared multiplied by k plus 1 squared. Butterfly effect. I'll expand this out. This is supposed to be k squared plus 2k plus 1, and then minus k squared. And then we cancel the terms. This is 2k plus 1 divided by k multiplied by k plus 1 squared. Now, let me just substitute this back to our limit. So this is k approaches infinity of ln of pi, and then multiply by 2k plus 1 divided by k squared multiplied by k plus 1 squared. Then we divide this with negative 2 divided by k cubed. So let's actually fix the denominator. So I'll flip the reciprocal and then negative distributes, and I'll factor out the negative ln of pi. So this is the limit as k approaches infinity of, so let's see, k cubed goes with the numerator, so k cubed multiplied by 2k plus 1. Then I divide this by 2k squared multiplied by k plus 1 squared. And I'll just cancel some terms out from here, so let's see, negative ln of pi. So this means we'll just end up with k and 2k plus 1, and then divide by 2 multiplied by k plus 1 squared. Okay, so now next, how about I distribute the k into here and the 2 into the k plus 1 squared. So this means this is negative ln of pi, and then the limit as k approaches infinity of, so this is 2k squared plus k, and then divide by, so let's see, this is, let me do this on the side, this is 2, then k plus 1 squared, that's equal to 2 times k squared plus 2k plus 1, and then this is 2k squared plus 4k plus 2. Okay, good. So now let me actually divide everything by k squared. So over here is negative ln of pi, then the limit as k approaches infinity. So do I divide everything from k squared, divide k squared to both the numerator and denominator? Okay, that's 2, and then plus 1 over k, and then we divide this by 2 plus, that's 4 over k, and then plus 2 over k squared. Okay, but now notice that if I were to plug infinity, so that means the limit as k approaches infinity of 2 plus 1 over k, and then divide that by 2 plus 4 over k plus 2 divided by k squared. It's just going to equal 2, so this is 2 plus 1 over infinity, that's going to go to 0, 2 plus 4 over infinity is 0, and then plus 2 over k squared, that's 0, and so we get 2 over 2, that's going to equal 1. Okay, so therefore this means, final conclusion is that, let's see, negative ln of pi times 1, and so therefore our final answer is just negative ln of pi. So that's our final answer. Pretty interesting limit if you ask me.